index 1.8. So I put this plot onto, this is a model for 1.8, and as you can see, the even for the best case focusing scenario in geometrical optics, these wavelength scale spheres still focus the beam more tightly as it propagated through the chain. I also looked at the optical transport in very distant parts of the chain. Close to the source sphere, because this is the source is isotropically emitting light, you expect to have a hard time coupling that light, and there's going to be a lot of attenuation in the first few spheres because it's so multi-directional. However, in very distant parts of the chains of spheres, it's kind of interesting to look at what the attenuation is like. And from roughly the 36th to the 40th sphere, we observed attenuation of about 0.15 dB per sphere. And if you look at the plot to your right, this is the same segment in geometrical optics as a function of index. And remember, this local minimalist shows you where you have focusing. So, or periodic focusing, the best focusing case. And we have even less attenuation in the best case predicted from the geometrical model. In conclusion, the physical optics case demonstrates stronger beam tapering and less attenuation than its geometrical counterpart. We can try to draw an analogy to explain these modes by looking at a geometrical model where you have TM polarization, or TM ray, incident at the Brewster angle. So according to Fresnel's laws, it won't experience, or there'll be zero reflection. And then if you have it so that it is also the Brewster angle at this interface, this ray will spatially reproduce itself as it propagates through the chain of spheres with no losses. So the rays that are near this are going to experience very little attenuation. And then also, since it's going to be passing through that vertex, it's going to have a very tightly focused spot. Still, the physical optics case deviates from this geometrical optics model, and that could be due to interference or diffraction effects because of its wave nature. And then also, during the self-assembly process, there's a material reflow with the polystyrene, which forms these microjoints, as you can see here. And recently, there have been groups that have studied this, and they've observed that there was a local enhancement of the E field at these microjoints. I would like to thank Dr. Ashtoff for his guidance and support throughout my undergraduate and so far my graduate career. My mesophotonics lab mates for their stimulating discussions and their help for me, coming over experimental hurdles. Adam Baran and Yang Chen, and I would really like to thank Orish because he's helped me out a lot over the past few years with modeling and then just as an experimentalist in general. I'd like to thank the Department of Physics and Optical Science for providing me with TA position over the course of the past year. Also, the NSF, NIH, and Army Research Office who have given us grants. Here's a list of publications that were developed in this work. Does anybody have questions?